This is somewhat an interesting paper, but as I said, I may not like necessarily agree with everything that this paper is trying to do, right? So this is a transaction paper, well, a distributed transaction paper, right? And the basic idea of this paper, the premise of this paper is to try to minimize the distributed transactions, like reduce the distributed transactions in your distributed database by trying to collocate all the partitions that are used frequently together on the same server, right? So instead of trying to run the two-phase commit across the partitions that may be on different replica sets and different servers, this paper tries to collocate the transactions in such a way that all these replica sets that are used in the same transaction, they have the nodes on the same server, and ideally it's not just the nodes but the leaders. Right, so here the paper has kind of an example. It's a bit difficult to try to grasp, but they narrowed it down to, let's say, just having 3 nodes, right? So it's a small like distributed system, and these 3 nodes have different partitions. So there is a partition P1. So node N1 is the leader, and then the partition P1, that's the follower. There is a partition P2, partition P3, P4, and I suspect there are like other nodes somewhere here, right? So like, for example, yeah, potentially, right? So what the paper is trying to do is when it runs the transaction, so here, for example, we have a transaction T1, right? It goes and tries to run this transaction. It has this transaction router. It has the planner. I will talk about it in a bit. But the basic idea is like this transaction will go to node N1, right? Because it was planned in such a way. And this transaction, it tries to access the objects X and Y. Yeah, I guess I have to write this down. So what do we have in their example? P1, P2, P3, right? Yeah. So we have these partitions P1, P2, P3. P1 has the object X, P2 has the object Y, and P3 has the object Z. Right? So if we have a transaction that tries to access X and Y, like the transaction 1, it will need to touch partition 1 and partition 2. And it happens to be the case that node 1 is the leader for partition 1, and also a follower for partition P2. Right? So in that case, what this system does, what Lion does, is going to take the partition P2, and it's going to transfer the leadership, right, from the old leader. So this is the old leader. It will transfer the leadership. It will remaster, right? Essentially elect a new leader, new primary, elect N1 as the new leader of partition 2. So now we have both partitions and their leaders co-located, and now you can run this transaction kind of locally, right? So it's on the same node, and you can avoid the distributed transaction, distributed two-phase commit. Now, the details are a little bit unclear here in terms of like how they actually run this transaction across multiple partitions located on the same node. In my mind, there still has to be some kind of two-phase commit, but regardless, it's kind of it is faster, right? Or maybe they just somehow just use a different, just sequentialize everything because it's on the same like physical machine. So that's the basic idea, right? Just like transfer the leadership if it's possible, right? So if for whatever reason you're trying to run the transaction and the node doesn't have all the partitions, so not only primary, but it doesn't have any followers, then Lion may decide to migrate one partition from one node to another node, right? So if I need to do this transaction, the migration is an option. That being said, they try to avoid doing this like online, right? So because they say that this migration takes like a lot more time than just changing the lira, which in my mind, changing the lira takes substantial amount of time as well. So they don't do the migration; they will run the two-phase commit, right? And then just like run this as a distributed transaction, but they will note that they record this information that, hey, we ran a particular transaction that access, let's say partition 1 and 4. Yeah, so if we have a transaction that tries to access partition 1 and 3, maybe some transaction T. Let me erase some of that stuff. Right. So if we have some transaction T3 that does operate on X and Z, right? So it will be partitions 1 and 3. There is no node that has, okay, a bad example. Let's make it X and A, and partition 4 has an object A, right? There is no node that has partition 1 and partition 4, so that will be like a distributed transaction. T3 has to be distributed. But it will collect this information that, hey, we had the transaction that accessed partition 1 and partition 4. It was a distributed transaction. We had to use distributed two-phase commit and OCC and whatnot. We will record this, and then we will use this planner component to adjust the placement or figure out the better placement, right? So not so much adjust the placement, figure out the better placement of partitions on the nodes. Right, so they identify all these transactions that were distributed, that access different partitions. They create a graph, and then they found like all the connections, all the connected components on that graph that represent the transactions that interact with like all the partitions at once, and then they will create with like a different placement plan for these partitions and start migrating the data. Right, and a good chunk of paper talks about like how to migrate the data, with regards to like how to figure out like the placement plan, right? So like where to put these partitions and where to put the leaders, right? Because it's in their mind cheaper to move the leader than to migrate the data. So they want to kind of pre-migrate the data based on the historical pattern, but they're okay like moving the leader like on the fly if there is a need. So this planner, its job is to figure out like the placement that will minimize the cost, right? To minimize the movement. So like not only optimize the transactions in a sense that most of them will be local, either because all the partitions have the leader in the same place, or you can quickly like migrate and whatnot. You want to make them as local as possible, and yeah, like minimize the migration. The final part that I think is important is this transaction router, right? So transaction router also keeps track of like what leaders have been moved, right? So if we run this, if we go back to this transaction T1, it used to be like partition P1 and P2, and then we had changed the leader. The next time a transaction similar to T1 runs that touches partition P1 and P2, the router will remember that, hey, this is the best node because I already did the remastering, right? Because I sent the previous transaction here, so probably it was remastered. Most likely, this is going to be the new leader now. So I'm going to send all of the similar transactions to the same machine if possible. Right. Obviously, you can overload the same machine, but arguably it's still like better than the two-phase commit because then you can overload like more than one machine. So yeah, I think this is kind of what it is in a nutshell, right? So instead of trying to run the two-phase commit transactions distributedly, the lion is trying to figure out the best placement of nodes in the system in such a way that we collocate the replicas of different partitions together in such a way that the transactions are likely to only like the transactions are likely to just have one node in common that has all the partitions that we can either elect all the primaries there or move the primaries as we need to. I'm gonna skip a bunch of these formulas and whatnot. I do want to show a few evaluation figures that they had, right? So they ran, let's say like YCSB, skewed workload. The bars are not so much interesting to me, but I do like to see like this graph, right? So line is the orange line, and this is variant hotspot workload. And variant hotspot position. So, as the workload changes, they need to like readjust their placement, right? And as the placement and migrations happen and like the plans change and all this readjustment happens, obviously the performance is going to suffer, right? And that's kind of what we see here, like a very big differences in the throughput that the algorithm can sustain, right? Much bigger differences than in like the other systems like Clay or two-phase commit doesn't even care, right? So in this case, two-phase commit is very stable. So, from one point of view, like I like the idea that, we can improve the performance by collocating stuff. But if we have those dynamic workloads, Lion needs to work very hard to adjust and start like moving the data back and forth, right? Adjust where the partitions are placed on what machines the partitions are placed. And that creates a very big variance in the performance, which I'm not sure I'm a big fan of. So I'm gonna stop